Okay, hi everyone. I'm Tiger. So I know it's cold and you're tired. I know some of you may not be able to attend the recitation. So I will have some of the explanations for our main concepts of recitation 3. So here you can see my screen here. Okay, so I'll show you how to need this again. So basically, I write everything in RStudio Markdown, and you need this to PDF. It will show you a PDF version of files. Okay, so today we are gonna talk about dummy variables, omitted variables, heteroskedastic, robust standard arrows. So first, let's talk about a story. Every regression is a story. So we want to estimate the effect of student-teacher ratio on test scores of the students. So intuitively, if student-teacher ratio is low, so one teacher will have fewer students. If the student-teacher ratio is low, you should have higher test scores, right? So we presume that the true equation is score is you have two parameters, right? Beta 0 and beta 1. And score is a function of student-teacher ratio, ST ratio. And we use OLS to estimate this equation. We use the right equation here, basically. And you have two estimators with the hat here. So beta 0 hat and beta 1 hat. So first you can load this CA school. I send this data set to you. And also you can use LM, is linear model, to estimate, to regress, basically regress the score on student-teacher ratio. And you can print the coefficients. So here you see a negative estimation for beta 1. Right. We usually just care about the coefficient on beta 1. So intuitively, this means that an increase rate of an increase of 1 unit of the student-teacher ratio will lead to, on average, a decrease of basically 2.3, decrease of 2.3 on test scores. And then we can see the negative relationship. If one teacher has more students, your student-teacher ratio will be higher, right? So you have lower test scores. We can see a negative relationship between them. And we can also check for the homoskedasticity, because for your normal t test to be valid, and your standard arrows, your normal standard arrows to be valid, you need this homoskedastic assumption. So what is homoskedasticity? Given different x values, the variance of your arrow term is constant. So basically here you can see for different value of student-teacher ratio, your arrows variance are basically same, constant. So we can say the homoskedasticity assumption here is verified. And then you can also print the 95% confidence interval and 99% confidence interval. So here it's very likely that your true parameter, at least your estimation of this true parameter, is negative. It's very likely it's between 3.5 and 1. And we usually use Stargazer. This package is very clean and neat to show the result of a regression. So here you can see it's a negative coefficient of beta 1, and this is a constant term. This is the estimation for beta 0. And you can see observations R square, standard error, F test. And usually you see 3 stars. 3 stars means this coefficient is very significant. This one is at 1% level, so it's very significant. You like to see the stars usually. And also you can print the confidence interval in the parentheses. Instead of here, you have the standard errors. And you just set the CI equals to true. You have the confidence interval of this estimation. And also you can see, you can just use the correlation function to have the correlation between student-teacher ratio and the test score is also negative. And here is the R square. For linear, simple linear regression, your R square has a similar interpretation as the correlation, but generally this is not true. For generally speaking, for multivariable regression, your R square is how much variation in Y is explained by your independent variables. Okay, so next topic is dummy variables. So here, maybe we should not treat student-teacher ratio as a continuous variable. Maybe we can see if we just like separate them into 2 categories. One is if you have a high student-teacher ratio, and then you have a low student-teacher ratio. So we set this dummy variable equal to 1 if you have a low student-teacher ratio, and 0 if you have a high student-teacher ratio. STR is greater than 20. So then we can test. We can first test if 2 groups have equal test scores. And this test shows that we have a very small p-value. So it's very likely that these 2 groups have a different test scores. So we can see in group 0, the mean is less than a test score. The mean test score is less than the mean in group 1. Which one is group 1? Group 1 is the one with low student-teacher ratio. Okay, so here is the result for the student-teacher ratio of dummy variable. So here you can see if you have a low student-teacher ratio, your score is on average increased by 7.2 basically, and this result is also very statistically significant at 1% level here. And you can check the code. Copy this. And here we will talk about heteroskedasticity. So usually homoskedasticity assumption is very important, but it's usually violated. Here in this example, maybe it's not violated, but generally you want to use heteroskedastic robust standard errors. So here mathematically, the conditional variance of ui given xi is sigma squared I, and we use the subscript I in mathematics to represent individual, like the individual value. So if we take this off, take the subscript I off, we have constant. So for everybody has a constant. Everybody has the same sigma squared. So unbiasedness and consistency of OS are not affected by the violation of homoskedasticity. What is unbiasedness? It's the expectation of your estimator equals to your true parameter, right? And what is consistency? It's the as your n goes large, the probability limit of your estimator is approaching to your true parameter. So the homoskedasticity assumption fails whenever the variance of unobserved factors changes across different populations. So here, if you write savings of a family, if the savings of a family is a function of your family income, right? Let's say if you're really poor, so basically you don't save, right? Very poor people, usually they don't have money to save. They just consume everything they have. But if you're rich, some people will save, right? Some people will save a lot, like Warren Buffett, and some people will not save. They will consume more. So if you're rich, if your saving is a function of your income, and if you're rich, you have more choices. So the variation for rich people, um, the variation of savings on rich people will generally be larger than the variation of savings for poor people. So you have heteroskedasticity here, and we want to use this robust standard errors to adjust for this difference. And here is how you do it. Coef test, linear model 1, and you just fill in linear model, your model's name here and here. And this will give you the robust standard errors here, coefficient. So this is different from the standard errors you see before, and they're also very significant. Okay, so our last topic is very important: omitted variables. So assuming that the true equation for score is it's a function of student teacher ratio, and the computer student ratio. So here, computer student ratio represents how much student can have the access to computers. So if this one is high, this means that on average students will have more computers, so they could potentially be more productive. So you may assume that beta 2 is what? Positive, right? If you have more computers, you should be more productive, and then you have higher test scores. However, you use the previous estimation, right? You forget about this. The true data generating function has two elements, but you only regress the test score on one of them. So this beta 1, should be biased, right? It should have two components. So this beta 1 now contains two components. It does not have a causal interpretation because it is biased. You can't say the effect of student-teacher ratio of score is this beta 1 right now, because it has two components. So first, it has its original beta 1 hat, n plus beta 2 hat times delta 1 tilde. So basically, this delta 1 is, you can just think of this as the correlation between x1 and x2. What is x, and we can test this, right? We can test this. So basically, we regress computer student ratio on student teacher ratio, and we see the coefficient, like their x1 and x2, these two are negatively correlated. So basically, delta 1 is negative, and beta 2, like we said, intuitively it should be positive. So your beta 1 tilde underestimates beta 1. It's underestimate beta 1. Right? So we can see the result here. So here you have a basically higher, like larger student teacher ratio. This beta 1 is uh, larger than this beta 1 because some of the effects are absorbed by computer student ratio, and this one's also statistically significant at 1% level, right? So you should always consider to add more control variables in order to avoid this omitted variable problem. Generally, you should do this, but causal inference is another course, another whole course. If you want to do a PhD, you're welcome to register for advanced econometrics, right? Okay. So here we also use the heteroskedasticity robust standard errors in parentheses. And I have all the code here. You can see how I did this in copy. Yeah. And also we have practice problems, textbook practice problems 5.1, 5.5, 5.6. You can do this when you have time, and you're welcome to come to me if you have any questions.